Okay, we're heading into the last lesson for Unit 1. Lesson 1.5, it's dealing with all word problems, and we're going to apply each of our three methods. So we're going to get another opportunity to solve by graphing, solve by elimination, solve by substitution. Okay. Before we do that, we want to talk a little bit about word problems. Oh, never mind. I kind of cheated a little bit with you. I gave you the answers already to the first section. But what methods can we use to help us solve a system of linear equations? There's 4 lines there, and you know 3 of them. But how would I solve a system of linear equations? How would I find the point of intersection? What tools do I have in my toolbox so far? What's that? Sorry? Okay, so we've got the first one you can solve it graphically. And then we have by hand. And we have graphically. You guys use Desmos a bunch, so that's using technology. By hand works if you have lines, linear equations that are already in slope-intercept form, y equals mx plus b. If they're more complicated and you still want to use graphing, then you're probably going to throw it in Desmos. Okay. What other options do we have?
Substitution.
Good. So that's algebraically. Substitution. Okay, that's when you isolate, for example, one variable on one side, and you have in terms of the other variable, and you can just substitute that in to the next equation. And the last way,
Algebraically by elimination.
algebraically, elimination. That's when we line up our terms, make sure we have the same value in the coefficient of one of the variable terms, and then we can add or subtract those equations together in order to eliminate a variable. All right, next in your notebook you have a little sentence that just asks you, which method would you use? So in that first one, think about it for 10 seconds, make your own decision. You're finding the point of intersection, or you're solving the linear system there. What strategy would you use? Any ideas? You could use substitution because you know that y is this. So you could just put that there for y. You'd end up with 3x plus 1 equals 4x minus 3. You'd be able to solve for x. That would work. Is that everybody's favorite? Substitution?
Yep.
Could you use elimination?
Yes.
Yes.
Sure. You do this, you'll eliminate the y's right off the bat. And you'll get x equals 4. Okay? Could you graph this one?
Yeah.
Sure. They're already in y equals mx plus b. You know the y-intercept of both equations. You know the slope of both equations. You whip that up into a graph, and you find out where the 2 lines hit. Okay? So you could use any of them on that one. That one you definitely... I mean, if you had to graph, then you'd be like, oh, sweet, Mr. B gave me an easy one to graph. Okay. But yeah, any of them will work on any of them, really. Second one there says x plus y equals 101 and 300x minus y equals 200. What strategy would you use? I might use elimination. I see that the y's are already lined up. All I need to do is add the equations. Okay, I'm going to end up with 301 x's equals 301. That's easy. X equals 1. Could I use substitution?
Yeah.
I sure could. I would just have to rearrange either one of these equations. Okay, I'd probably rearrange equation 1 in order to isolate x or y. Let's say I isolated x, I'd get 101 minus y. And then I would just sub that in everywhere I see an x in equation 2. Yeah, but elimination is probably the easiest one there because it's already set up and lined up and all that good stuff. So that's what today is about. It's being able to choose the best method. We're going to talk through choosing the best method, but then I'm just going to end up doing it whichever way so that we can practice one more of each before you move on to your assignment and your test for the unit. So let's dig into example 1 there. Example 1, graphing, substitution, or elimination. We get to choose. Okay, we're looking at this word problem and we're going to probably underline some important information. I'm going to jot down some important information as we go along. We've got Christian. He has a total of 8 cars and trucks to play with. 8 cars and trucks to play with. His birthday is soon. He hopes to double the number of cars he has now. If he does this, he'll have a total of 11 cars and trucks. How many cars does he have now, and how many trucks? So it's a bit of an awkward question. You've got cars and trucks together is 8, and then when he's all said and done, if he doubles the number of cars, then cars and trucks together will be 11, okay? Well, before we go into picking a strategy, what do we need to do anytime we are approached with a word problem?
Variables.
Variables. Let's introduce some variables. What are we talking about here?
Cars and trucks.
Cars and trucks. Those are our unknown values. How many cars he has, how many trucks Christian has, okay? So we've got let C be the number of cars he has now, and let T be the number of trucks he has now. What's our next step?
Write the equations.
Right, 2 equations. All right, let's see what we have. Well, right now he has a total of 8 cars and trucks. Cars and trucks together is 8. Can you put that into an equation? I hope so. C plus T equals 8. Now our next equation is a little bit tricky to think about. You have to remember that C represents the number of cars he has now. What is he hoping to do on his birthday? Double the number of cars. So he's going to end up with 11. Then, yeah, good. The number of trucks isn't going to change, but he's hoping to have 2 times the number of cars. Okay? You could probably just think this through and get the answer right now. The number of cars is going to double, and he's going to have 3 more altogether. Anyone know how many he's starting with? If he gets 3 more from doubling it, how many must he have started with? 3. He must have started with 3, because he's going to double it and get 3 more, so he must have started with 3. Anyway, you're going to get 3 and 5 at the end of the day. I look at this and we're talking about trucks and cars. Are we going to get half a truck or half a car? Are we going to get 0.7 cars? Not going to happen, right? So what method could we use for this one?
Elimination.
Yeah, we could use elimination. That'd be really easy. Substitution would be really easy. Guess what we're going to use?
Eliminate.
We're going to use graphing, okay? I know it's whole numbers, and it's an easy one to do. So I'm going to use graphing, and it actually ends up being, well, whatever. We'll see when we get there. So I'm going to graph both of these lines, and we're going to graph them using their intercepts, because the axes actually becomes a little bit interesting. I'll draw it off to the side. Do you guys have a grid there as well?
Yeah.
So I'm going to go cars along my horizontal axis, and I'm going to go trucks along my vertical axis. I've got 0 down here. And then you can do each box as 1. If I got this question on a test, I would never graph it. Do I need to think about negative numbers? Nah. He's not going to have negative cars. We already know he has some. And I need to keep going. You need to get up to about 11 here. All right. So you're looking at these and you're saying, Mr. B, I really don't want to graph those because there's no x's and y's. It's not in y equals mx plus b. It's cars and trucks. How do I graph cars and trucks? Well, I'm not going to use slope-intercept form. Instead, what I'm going to do is use another method for graphing, which is determine the intercepts. Okay, so I'm going to determine the intercepts of equation 1. How do I do that? If I want to find the c-intercept, what do I need to do?
You need to multiply the t by 0.
I just need to say t is 0. Okay, all along this line, the value of t is 0. Okay, so I'm just looking at if they were all cars, how many cars would he have? C plus 0 equals 8. C equals 8. So if all of Christian's vehicles were cars at the start, he'd have 8 cars. Okay, that's our c-intercept. Well, what would it be if all of them were trucks? We'd be finding the t-intercept, where none of them are cars. C equals 0. So if they were all trucks, we'd have 0 plus t equals 8, which is just t equals 8. That's up here. All right. I have 2 points, which allows me to do what? Draw a straight line through those 2 points. Yours will be prettier than mine, but that's okay. There it is. And now let's do the same thing for equation 2. Now in equation 2, I'm going to solve by intercepts again, or graph using intercepts again. So I'm going to find my c-intercept by doing what?
Y equals 0.
Setting t equals 0, sorry. So c-intercept, I get 2c plus 0 equals 11. That's going to give me a 2c equals 11 and a c-intercept of, I'm going to use decimals, 5.5. I could just write 11 over 2. So where's that? 5.5 is right there. Right in the middle of 5 and 6. 5.5. The t-intercept occurs where? Where c equals 0. So again, we're considering, okay, what if all of these 11 after his birthday are trucks? Okay? Then there would be no cars, which means he would have started with no cars, because if you double, he's doubling it. So he must, anyway, carrying on. T-intercept, we've got 2 times 0 plus t equals 11. Well, 2 times 0 is 0. That just leaves me with t equals 11. So that's my t-intercept for line 2, my purple line. I've got 2 intercepts, which means I can draw a straight line. And on your graph, you should be able to see that those go right through the point 3, 5. Okay, so my horizontal axis was cars. This tells me that at the beginning of the situation, currently, before his birthday, Christian has 3 cars and 5 trucks. Christian has 3 cars and 5 trucks. Okay? I could double check this in my other equations, in both of the equations, or I could just think this through. Is 3 plus 5 8? Yep. If I double the number of cars on his birthday, I'll have 6 plus 5. Is that 11? Yep. Good enough. Okay? So again, we solved by graphing, but you could use substitution, you could use elimination. You're actually better off using those other methods. It'd be faster and easier, and you wouldn't have to worry about graphing. Okay, example 2 and example 3 are much more difficult. Okay? Okay, example 2 and example 3 are much more difficult, and you do need to know how to do them and how to do them on your own.
Can you go a little bit slower?
Yes, I'll try to go a little bit slower. So we've got example 2, solve a distance, speed, and time problem. So distance, speed, and time are related to each other. They form an equation that you use in science quite often. We'll get to that in a second. But let's just talk about the situation that we have. We have a canoeist. She's going down a river. So I'm just going to go ahead and draw myself a river to help me think about it. Okay, this is example 2. A canoeist took 2 hours to travel 12 kilometers down a river. So the current is going this way. She's going down a river with the current, and she's traveling 12 kilometers. 12 kilometers, and it takes her 2 hours. Then she's going to turn around and come back up against the current. How far is she going to travel? She's going to travel 12 kilometers against the current, and it's going to take her 3 hours. Does that make sense? It takes longer to travel against the current than with the current. Why is that?
Because it's always pushing against your faster.
So it's your speed minus the current when you're going against the current. And when you're going down the river, it's your speed plus the current. Ah, very helpful advice there. What's our goal? We want to find the average paddling rate. So we want to find the canoe's speed in still water. Perfectly still water, no wind. How fast would this canoe be going? Okay, that's not how fast she's going in this case, upriver or downriver, because she's with or against the current. And then we also want to find the speed of the current. What's my first steps typically when I'm working on word problems? Introduce variables. Introduce variables. Well, I look at the problem. What am I trying to find out? I want to find out her paddling rate, and I want to find out the speed of the current. So I've got P and C. We're happy with that? Let P be the paddling rate. You could say in still water if you wanted to. Probably don't need to. But we should indicate how are we going to measure this? How is her rate going to be measured? Units of measurement. Kilometers per hour in kilometers per hour. And we're going to let C be the speed of the current. How are we going to measure that? In kilometers per hour. All right. So again, going downstream, she's being helped by the current. Going upstream, she's being opposed by the current. So let's set up our equations. Set up 2 equations. And in order to do that, we're going to use a little bit of a grid, a little bit of a chart. Okay, we're going to think through this. We got, and you can copy this down as I'm drawing it. Direction, distance, speed, time. She's going downstream. To help me out, that's with the current. And then she's going upstream. And to help me up, that is against the current. I'll give you a second to catch up there. Okay, so filling in this chart is going to help us establish 2 equations. So let's just think about what we know. Whether she's going downstream or upstream, do we know the distance that she travels?
Yes.
Yes.
12 kilometers.
12 kilometers. So I'm just going to put 12 in here. I'm going to note that it's measured in kilometers per hour. They're both 12. Do we know the time it takes in either case? We sure do. Okay?
Yeah.
Downstream, 2 hours. I should note that this is measured in hours. And upstream, we have 3 hours. Now, do I know the speed of the canoe going downstream?
Yeah.
No. Do I know the speed of the canoe going upstream?
No.
Do I know the speed of the canoe in terms of P and C?
Yes.
Could I express her speed using P and C?
Yeah.
Downstream, how fast is she going using P and C?
6 kilometers.
You don't know what P or C is.
Can we guess?
Nope, that wouldn't be helpful at all.
Wait, but we know how fast
When you're
she's
going No, you don't. When you're going downstream, you have the speed of the paddling plus the speed of the current.
Which equals
P is the speed of the paddling, C is the speed of the current. Oh, when she's going downstream, she's going P plus C. Okay, you don't have a value. You don't have an answer for that yet. You have it in terms of the variables. That's the point of variables, they're unknown values. What about going upstream against the current?
P minus C.
P minus C. Whatever she paddles, the current is going to take away, and that's why it's going to take her longer to accomplish it. So now please pay attention as we set up our two equations. We're going to use, maybe I'll make a little note off to the side. Note distance equals speed times time. Distance equals speed times time. If you travel 6 kilometers an hour for 1 hour, your distance traveled will be 6 kilometers. If you travel 6 kilometers an hour for 4 hours, your distance will be 24 kilometers. Okay? Distance equals speed times time. Well, that's how we're going to set up our equations. So we're going to have equation 1. We know, and that's going to be our downstream equation. We know that she's traveling 12 kilometers. That's right here, distance. 12 kilometers. Well, what is she doing? Well, she's traveling at a speed of P plus C for 2 hours. She's traveling at a speed of P plus C for 2 hours. So it looks like this. 2 times P plus C. Downstream, she will do P plus C for 2 hours, and she'll get those 12 kilometers. What about upstream? Go ahead and try and write the equation for upstream. Check back here when you're done to see how you did. Okay, in order to travel those same 12 kilometers upstream speed is going to be P minus C, and she has to do it for 3 hours. If she does that, she'll get 12 kilometers, just like she got 12 kilometers going downstream for 2 hours. Now, next step, solve. We can use substitution or we can use elimination, but before we even get to that, I'm looking at both of these equations and I'm thinking, they're kind of ugly. P and C are trapped inside groups. I can't really just, you might be tempted to line it up and add the C's to cancel out, and then you got 2 P's, and I don't know how you would add those factors and add that, okay? You can't do that because P and C are trapped inside these groups. We need to undo these groups first. Now, what you know from your past algebra experience is you might think, okay, I'll just distribute and that will eliminate the brackets. That will work, okay? That will work. It's not the best way to do it, but it will work. How else could I, just looking at equation 1, how could I simplify equation 1? Any ideas out there?
2 PC. Oh, never mind. That's not-
Think of this as one thing. Think of this maybe as the variable x. What do I have now? I have 12 equals 2x. How do I get x by itself?
You just
Divide both sides by 2. So I can isolate this group by simply dividing this whole side by 2 and this whole side by 2. That's going to leave me with equation 1. On the right side, I'm just going to have p plus c. That's nice. And on the left side, I'm going to have 6. 12 divided by 2. Okay, so I've divided this whole side by 2. And then I have to do the same to both sides. Well, let's think about that in terms of equation 2. I think of this as one group, one thing. It's being multiplied by 3. Well, how do I get that thing by itself? It's b. Thank you. It's being multiplied by 3, so I take the inverse of multiplication, which is division. I divide both sides by 3. On the right-hand side, that leaves me with p minus c. On the left-hand side, I have 12 divided by 3, which is 4. Aren't those nice? Hey? Look at that. Haven't changed a thing. All right. What would I do from here? From here, I would probably use elimination. Okay? Yeah, I would certainly use elimination. So let's do that. I already have my p's lined up and my c's lined up. Does it matter which one I eliminate? No. It's only going to be determined by the sign that I put here. Would you like to put a plus sign here or a minus sign here? A negative sign? Sure. Then we're going to have 6. Take away 4 is 2. P take away P is 0. C take away negative C. That's C plus C, which is 2C. Which tells me that C equals 1. What have we determined so far?
That C equals 1.
What does that mean?
That the current is 1 kilometer an hour.
Yeah, the speed of the current is 1 kilometer per hour. Okay? Speed of the current is 1 kilometer per hour. Let's carry on to next step, which would be substituting our answer for C into any equation. Okay? Doesn't matter what it is. So maybe let's just look at equation 2. We're going to sub. We've got 4 equals P minus C. We know that C equals 1. So we've got 4 equals P minus 1. We're going to add 1 to both sides. P equals 5. What does that tell us?
That was 5 kilometers per hour.
Yep. So we have our two answers. We have our solution. So we're going to check, think through that it actually made sense, which you already know what those things mean. We can go back up here to see if it works. In equation 1, P plus C, 5 plus 1 is 6 times 2 is 12. Yep. P minus C, 5 minus 1 is 4 times 3 equals 12. Yep. So now you can see she's working 5 kilometers an hour. Downstream, she gets to add a kilometer per hour to that. 6 kilometers per hour. She's going to get 12 kilometers in 2 hours. Upstream, she's paddling the same speed. She's not working harder or less hard, but the current is working against her. 5 take away 1. She's going to be 4 kilometers per hour times 3 hours, 12 kilometers. Okay? The average paddling rate is 5 kilometers per hour, period. The speed of the current is 1 kilometer per hour. Okay, what was tricky about this one? Setting up the speed. Both variables were needed in order to set up the speed. You didn't know the speed, but you knew it in terms of P and C. So you just have to be able to think through problems like this. Oh yeah, downstream is going to be her speed plus the water speed. Upstream is going to be her speed minus the water speed. Okay, that's why we set up our variables. set up our two equations. A little trick for simplifying them is to consider this as one group, which it is. Divide both sides by 2 to simplify. Then solve. We used elimination. Sub back into one of the equations. Double check it in your mind. Bada bing, bada boom. Finish with a statement. Okay, example 3 is a mixture problem. Example 3 is a mixture problem. We're going to have two solutions being mixed together, and we're going to know some things about them, and we're going to know some things about the final solution that gets made. A solution is just a mixture, like a liquid mixture, okay? So we have Miriam. She has one bottle of 5% acetic acid. I'm going to give her a little bottle here of 5% acetic acid. And she has a bottle of 10% acetic acid. %, solution. Well, what's she going to do? How much of each should she use to make a 250 milliliter mix of 8% solution? So she's going to pour it in to another container. She's going to pour some of this and some of this. And at the end of the day, she wants to have an 8% solution. And she wants, maybe I should write this, she wants to have 250 milliliters of an 8% solution. Okay, is that picture helpful? And we're trying to figure out the amount from this jar and the amount from this jar that will make that happen. Okay, so let's introduce some variables. What is unknown?
How much percent of this?
Not how much percent,
How much
just how much.
milliliters?
How many milliliters, just how much. Okay, so here we have, let's name this bottle F because it's 5%. Let's name this bottle T because it's 10%. And we're going to let F be the amount of 5% solution added. Okay, so technically F should be, this arrow represents F. It's the amount that gets added. And we're going to let T be the amount of 10% solution added. So there we've got T. All right, well, let's think through this. The next step is going to be set up two equations. Set up two equations. And I have some ideas of what's going on here. I could use a chart to help me understand it again. Basically what we have is percents and amounts. Okay? That's the two things that we have. Now if we're talking about F and T being amounts, what's going to happen if I take F plus T? What's my goal for the amount?
250.
See? Okay, so we've got equation 1. That one's not too tough. Okay? I'm going to put some F in there. I'm going to put some T in there. And at the end of the day, I'm going to have 250 milliliters. I don't know what F and T are. Doesn't matter. That's the point of setting up two equations. Now, the other thing that I know is that I want to have 8% when I get to the end. Okay? This part is a little bit tricky. I need to consider the volume of pure acetic acid. Okay? This bottle, only 5% of it is pure acetic acid, which means 5% of what I pour into my new container is going to be pure acetic acid. From this bottle, whatever I pour in, only 10% of it is going to be pure acetic acid. Okay, so I'm thinking in terms of how much pure acetic acid I'm looking for. Well, in my final solution, only 8% of it is going to be pure acetic acid. Could I find out exactly how much pure acetic acid is in that final solution?
Yeah.
Yeah, I have all the numbers. 8% of 250. So watch this. Equation 2. I'm going to set it up piece by piece. The first part is that I'm going to have this 250 milliliters, but I only want 8% of it to be pure acetic acid. Equation 2 deals with the amount of pure acetic acid in each solution, in each bottle. Okay? Well, here's a question for you. If 8% gives me 0.08 times 250, what is 5% of F? How would I write that? 5% of F
0.05.
times F. Out of this F that I put in, the amount, 5% of it is going to be pure acetic acid. What about the T? 0.1 T. Okay, now I have two equations and two variables. I can simplify equation 2 a little bit better. So I'm going to do that right away. Just copy down the left side, 0.05 F plus 0.1 T. And 0.08 times 250, I would do in my calculator. It comes out as 20. So in this final solution, 20 milliliters is pure acetic acid. Okay? And we've done graphing, we've done elimination, so let's do substitution. In order to do substitution, I need to express one variable in terms of the other variable. So what I'm going to do here is I'm just going to take equation 1 and I'm going to subtract t from both sides. That's going to give me F equals 250 minus t. Okay, so I'm kind of done with these two original equations. I now have a rewritten 2 and a rewritten 1. 1 has F in terms of t. So what can I do now? I can sub F. I can sub this side in for F anywhere I see it in equation 2. So I'm going to take equation 2 again. This is the same as you've done before, by the way. It's just a little bit uglier numbers. And instead of F, I'm going to write 250 minus T. Over here, I still have 0.1 T equals 20. And now I have one equation, one variable, so I can solve it. I'm going to distribute my 0.05 to both terms here. Okay, 0.05 times 250. You do that in your calculator, you would get 12.5. And minus 0.05 T, copy down the rest, plus 0.1 T equals 20. Now I notice that I have T's, okay? I have 0.1 and I have 0.05. I can kind of think about this as like 10 minus 5, okay? It might be hard to see, but you could also do this in your calculator. What does that give me? It gives me 12.5 plus 0.05 T equals 20. I'm working a little quick just to get it done. Subtract 12.5 from both sides. Leaves me with 0.05 T equals 7.5. Divide both sides by 0.05 T, which you would do in your calculator. You'd get 7.5 divided by 0.05. And my last line, I don't have enough room, so I'm going to just write it over here. T equals 150.
No.
Well, let's think about what it means. T is the amount of 10% solution. So what should we measure it in?
Milliliters.
Milliliters. Okay? Before we go ahead and think about that, let's go back and find out how much of the 5% solution we have. So that's equation 1. I'm going to use this guy down here. F equals 250 minus T, which is 250 minus 150, which is 100. What does that tell me?
F equals 100.
Miriam needs 100 milliliters of the 5% solution and 150 milliliters of the 10% solution. If she does that, she'll get 250 milliliters of an 8% solution. Your practice problems are noted for you on the bottom of that workbook page. They come from page 44, numbers 4 through 6, 8, 10, 11, and then 13 through 18. They're all word problems, so you'll be introducing variables, drawing pictures to help you think through it, setting up two equations, and then solving it out and checking back to the question to make sure it makes sense and what you did makes sense, okay?